The main question that was at the base of creating Toffee was, what is the best design? What is the optimal design to fully exploit the capability of 3D printing? The majority of the market is still using a traditional manufacturing technique, stamping, molding, casting, and machining. In the case of Toffee, we extended our technology on the core, on the mats, on the model.
Where do you see Toffee going in terms of capabilities?
If you see at the space, an abstraction of the space in the design workflow and all the space of design for manufacturing a CAD system, there are many gaps that are still empty, and there is space for us, for other players in the space to fill there. The engineer is still the center of the design process. We have a strong advantage. Toffee is not replacing existing software. Toffee is not replacing the engineer. Toffee is augmenting what is the design workflow. Our value is still the human, the people first. There is so much more you can do to optimize a system, to optimize a series of components without touching the key component. The core of these techniques is topology optimization, which is historically physics driven. When we then extend to generative AI, we tend to think much more a data-driven approach. In this context, I strongly believe that the solution is hybrid.
Ladies and gentlemen, I have Marco on the show today who will talk about fluid topology optimization. Welcome.
Thank you, Jousef. Hi.
Really cool. Can you give the audience a little bit of a background? Like, how did you come up with the idea of ToffeeX? What are you guys actually working on? And what is the vision, but also the mission of Toffee?
Yeah, sure, Jousef. So first of all, thank you very much for inviting me. Very excited to have this opportunity to go deep and dig and explaining in detail what was my journey and a bit more about my technology. But background, I'm a mathematician. As you can tell from my accent, come from Italy, from a small village close to Rome. That was kind of my little prison, not much to do, but the maths brought me to study optimization. It brought me to London, where I did my PhD at Imperial College in the Department of Aerospace, and where I developed what is today still the core technology of Toffee. The journey was pretty much starting from pure maths and then going to applied maths, then physics of fluids, and then aerospace. So moving from theory towards more applied, more to be closer to industrial problem. When I was at during my PhD, it was let's say 2015 between 2015 2018. It was really the 3 years when the industry realized the value brought from additive manufacturing, especially metal 3D printing, was very promising. I remember it was really 2015 when Siemens for the first time managed to 3D print a turbine blade for so a critical component for but just by using the 3D printing. So then there was a huge gap in the market. So the possibility of creating or seeing in the future the possibility of creating pretty much everything using 3D printing, and the lack of a proper way to fully exploit the 3D printing capabilities, the lack of a proper way to find what is the best design unconstrained by the traditional manufacturing technique. So I would say the main question that create a milestone on creating Toffee, the main question that was at the base of creating Toffee was, okay, what is the best design? What is the optimal design to fully exploit the capability of 3D printing? What is now the best design for coolant system, for gas turbine? What is the best design for heat management for batteries? Together with my co-founder, that was my supervisor during my PhD, we decided to, we managed to get some traction from first, let's say, industries, and we decided to spin out from Imperial College. And that was really the beginning of the company. Since then, the vision further evolved. As I would say, at the beginning, the answer was like, what is the best design to fully exploit these new techniques? But then we very quickly realized maybe the market is still not ready to embrace so quickly additive manufacturing. Maybe additive manufacturing, especially for critical components, is still very related to deep innovation in the industry. The majority of the market is still using a traditional manufacturing technique, stamping, molding, casting, and machining. So it doesn't matter. Now the technology was ready, the core of the technology was strong, so we adapt the technology also to traditional manufacturing technique. And since then, the vision has further evolved. And now the vision of Toffee is providing a tool to the customer, to the user, to the designer, a tool to massively accelerate the R&D cycle, the innovation cycle, and bringing the customer much farther and much faster to very innovative design that are suitable with any manufacturing technique.
Mm-hmm. This is super insightful. There's a lot of things I want to unwrap. So one of the things I noticed, especially when you're in the space, you have a look at solutions like Toffee and some of your competitors out there. They come up with fancy and filigrane structures, but most of them are not manufacturable. But this is not the case with Toffee, right?
Yes, exactly. The problem of manufacturability, I think, is a shared pain in the field. There's always the fight of finding the soft spot between finding the best optimal design for operation. So the design that is physically the most efficient, and then finding the design that is efficient in the meaning of the user. So for the user, efficient doesn't mean the best heat exchange, the best reduction of pressure losses, for example. For the user, efficiency means, this design has to be light, has to be manufacturable within $1, for example, or has to be manufacturable with this machine and not with this machine. So this is really, even though it is an industrial problem, it's still a mathematical problem. It's just way bigger and way more complex. In the case of Toffee, we extended our technology really on the core, on the maths, on the model, to include this strong constraint. So literally today, the user can click from the platform, from the user interface, what is the manufacturing technique of choice and all the related parameters. For example, with Toffee you can create design that are suitable for 3D printing, and you can select the resolution of the 3D printing, you can select the material, you can select the overhang, so to create a self-sustaining, self-supporting structure. And then for machining, for example, very similar. You can select that. You can select the tooling size. And Toffee optimize, so use the physics to drive the optimization within the constraint of your manufacturing technique. So really, the vision is creating design that are real, creating design that are manufacturable and really useful for the customer. So in this context, I truly believe that to be a useful tool for the customer, a tool that is accelerating the design cycle, there are two main ingredients. The one I just talked about, so the design, the output has to be real, has to be manufacturable, or at least very close to be manufacturable, and then leave to the engineer, to the designer, the last refinement, for example. And the other ingredient is the speed. The design has to be produced, the iteration has to be done in a short time. So I always talk to my team, when I have to align the next step, the next, let's say, decision in terms of development, with this word, like, guys, we need to, let's say, leave the black box mindset. Something that I always call the black box mindset with my team. So we don't have to think AI, we don't have to think the new methodology as a black magic box when we ask we wait for days, for weeks, and then we have an answer. We need to create a tool that is accelerating. Our value is still the human, the people first, and we have to create a superhuman. So we have to create a mix of simulation, AI, data to accelerate the process of R&D and transforming what is really transforming the time the engineer is using, shifting from spending months on finding one suboptimal design to the time of the engineer using Toffee for navigating through many optimal design, many optimal trade-off between efficiency, between cost of manufacturing, and shifting the role of the engineer towards a more system level optimization. And I truly believe when you shift through a system level optimization, you literally see the problem more from apart, and you can tackle bigger problem. You can see more complexity, and this will make the step towards net zero, decarbonization, energy transition, etc.
It makes a lot of sense. From a theoretical, like how you explain it, it sounds too good to be true. But depending on when this episode goes live, we will have a deep dive session with Anto, one of your colleagues, and he will show ToffeeX in action, so people can actually ask questions interactively. It's going to be a dynamic session. So I think people have to see it to actually believe it. So I think that's going to be really, really cool. And one of the things I want to go back to in the introduction, you mentioned like you had theoretical mathematics, applied mathematics, and then suddenly there was a spin-off. I want you to talk a little bit more about this kind of entrepreneurship mindset and how much the good sides, but also the bad sides, because obviously there went a lot of work and sweat and tears into what today we call Toffee and you see as a nice product. But I want you to talk to the audience maybe about like the struggles and things that haven't worked well, because I think you see a product, right? But there's a lot of research that also goes not only into the algorithms, but also on the usability point of view.
Yeah.
To make sure an engineer can use these algorithms to actually democratize, for example, a generative design. Like, how was it for you, that struggle?
Yeah, it was painful and it was long. So it's really what you described. It's really the shifting towards having a technology and having a product. There is a massive difference. There is a massive reasoning, especially in terms of understanding the market, understanding the psychology of the user, but really what is useful, the difference between what we believe is useful and what is really useful for the industry. So to give more detail about the journey, the project, let's say the technology has been developed during research, university research, so academia research. So the focus was really on finding new methodology, new results that made sense under mathematical and physical point of view. The key point, the key difference has been collaborating through the university with industries. So even before finishing this academic journey, we had already couple of industry interested and using the technology. And really the key there was driving the technology, saying this is where the industry is moving towards, and you can apply this to, in that case, was specifically for the optimization of the internal coolant channel for a gas turbine. After that, really, the transition between technology and product was not even started. We decided to jump in the dark, really, that's what I call it, and found the technology. We found an investors that believe in us and put the money to hire more people. But really, the very 2 years of Toffee has been focusing on the technology. We were 6, focusing on improving the technology and finding what is the match, how we can apply this technology, this optimization of components driven by physics for the customer, for the user, for the application on industry. Only after that, after gathering pieces from the industry, we realized, okay, the human wants to be at the center. The engineer is still the center of the design process. So we need to wrap up this technology in a way the engineer can use the software on its own. So we create the platform, we create the product, we give to the customer the possibility of clicking among all the feature of the manufacturing constraint, etc., all the objective. And then really, I would say Toffee as a product started. And this was not even 2 years.
Mm-hmm. I was wondering, how do you communicate to the end user? I mean, the engineers are sometimes open-minded, but sometimes they also are going to be like, well, never change a running system, right? Like, how do you talk to the engineers? Like, how do you show them the value? How does it facilitate their life? But also to the decision makers who are sometimes also maybe a little bit close-minded. How do you approach this problem?
So, many aspects, many things to discuss here. So, first of all, there is always a cycle, let's say, a process of education of the market. So there are, as you say, some customers that are very happy and embrace the vision like in seconds, and some customers that requires more evidence, more strong evidence of the advantage of using Toffee or in general a new technology. We have a strong advantage that Toffee is not replacing existing software. Toffee is not replacing the engineer. Toffee is augmenting what is the design workflow. Our user will still use CAD software. We still use simulation software for flow dynamics and for structure. Toffee literally plug between these two groups in the design workflow and speed up the design cycle. Usually the design cycle is centered around the designer that use the CAD tool to design, to shape any component, to fix the idea, a coolant system for a battery. And then the design is passed to the analyst to make a flow dynamic simulation, structural simulation, and then it's improved by coming back to the designer and again. And this cycle we know are slow and literally never ending. By plugging Toffee here, you can directly find in hours what is the optimal design, or at least something that is a very good starting point. But the user will stay there. The engineer will stay at the center. The software upstream and downstream will remain there, but they will be used on product that bring much more value. So really, the user doesn't feel displaced, doesn't feel that they're going to replace the user with a machine. And it's really reduce the resistance from the user to adopt Toffee. In terms of, let's say, decision maker in the company is much easier. Toffee is strongly associated to sustainability, to accelerating innovation, to accelerating the go-to-market of a product. And from the decision maker, knowing you can add tool to speed up and to reach your objective faster is definitely very, very appealing.
Yeah, that makes sense. Cool. I mean, from a feature point of view, like how can you walk us maybe through one of the use cases, how someone would use Toffee, maybe for heat exchanger design, maybe, I don't know, reactor design, something like this. How does it work, like from beginning to the end? How would a user go through the software?
Yeah, this comes really back to my previous answer. Let's say, very in a nutshell, the output of CAD software are the input of Toffee. So you really start from a box, from a design space. Can be as intricate and complicated as you want. Can be a pipe, can be a cylinder, can be a cube. But really, it's the space where you want your component to be designed by Toffee. This is the setup, which is very familiar to the environment of the designer. So you really start from a 3D visualizer. You can play with this, let's say, digital empty space. Then the user has to set the physics around this environment, has to specify what is the physics that is governing the functioning of this device, of this component, and literally tell the software, I want to optimize this. I want this component to work and improving this aspect. So you can imagine to fix the idea having, for example, to fix the idea for the coolant system for thermal management for batteries, for example, uploading what is the space around the batteries you want to create your design system, your optimized component. Asking to the software, this has to be governed by flow dynamics. This is the fluid. This has to be governed by heat equation, so the energy equation. I want this component to be manufacturable with this technique. I want this component to have this material, etc., etc. And then simply clicking go. And Toffee, in a matter of 1-2 hours, will give you the best optimal design for your constraint. And you can also automate and getting a series of design with different, let's say, trade-off. Something that is more efficient on manufacturing costs, something that is more efficient on, let's say, on mechanical losses, on the energy you need to the functioning of the component. Together with the design, you get also the analysis, so the thermofluid analysis of the component. And then this is, let's say, the end of the space of Toffee in the design workflow, and then it's up to the user really going to manufacturing, going with further analysis, or iterate again.
Mm-hmm. That makes sense. Really cool. Anything else you want to add?
Yeah. You touch on what are the capabilities, what are the physics. So I mentioned that the user can select the kind of physics on the kind of objective from a component, and we are a multi-physics, so Toffee is multi-physics, so the user can really click between optimizing for flow dynamics, optimizing for heat exchange, but we extended also towards other physics, like the physics of mixing, the physics of chemical reaction for absorption and adsorption of gases, which is strongly used today for devices of carbon capture. And in terms of objective, it's really around how to shaping the streamline, the fluid to hit, for example, heat efficiency, thermal uniformity, which is of key importance to optimize also reliability, especially in aerospace, to optimize flow uniformity. We realize sometimes that there is so much more you can do to optimize a system, to optimize a series of components without touching the key component. Imagine I have a heat exchanger, a system for heat management. I can optimize the efficiency of the heat management system even without touching the heat exchanger, but playing with the collector, with the manifold that are delivering the fluid to the heat exchanger. So it's a matter of optimization on upstream and downstream fluid, and to control the shape of the fluid, the uniformity of the fluid inside the system. So part of our customers are using this to further optimize more on a system level. Also, you can play with more than one fluid at the same time, which is opening all, let's say, the optimization, the design of fluid heat exchangers. In that case, mostly optimized for compactness. So I want to find the most intricate structure of the two fluids to remain separated, but to exchange heat in the most compact way. And the list is it's long.
Uh-huh. I'm wondering, from a mathematical point of view, Marco, how much do you want to delve into it? Like, I think the audience would be interested you have an incredible solution, right? But there's also competitors out there who can't do the same. So I don't want you to give away the secret sauce, of course, but how does it work from a mathematical standpoint? Also the optimization algorithms.
So obviously I won't go too much in detail. I would say, it has been hard work and a mix of obviously theory around CFD, so computational flow dynamics, the theory around how the algorithmic theory behind flow dynamics. So really understanding how the iteration of the solution of the simulation of the physics works, then together with, and using that information with an optimizer, which is, that is the secret recipe, that is embedded with let's say the simulation cycle. It's not just a theoretical model, there is much more in terms of control theory, especially to stabilize the process. We are dealing with equations, we're dealing with physical systems that are unstable, or at least when it's a matter of simulating, you can easily trigger instabilities. And when it's a matter of optimization, it's even worse. When I mean instabilities, it's really what I mean is like you have a perfect algorithm, you click run, after 3 seconds, it doesn't work anymore because you are simulating something that is unphysical. And this is very common, and this is the struggle on creating the software stable. So I would say it's not only about the theoretical optimization model has been 80% of the work on making the solution converge into something meaningful. So there is a lot of control theory there.
Mm-hmm. That probably cost you a lot of headache when you were developing this. And okay, see, right now we're in 2024. How do you imagine, what are some of the limitations maybe of Toffee ways? Think maybe in 2030, looking forward, something that needs to be solved for the engineers, because although it seems like a perfect solution, how you described it, maybe there's something missing, and maybe looking forward like 5 or 6 years, where do you see Toffee going in terms of capabilities?
Yeah. There is so much more. Like even if you see at the space an abstraction of the space in the design workflow and all the space of design for manufacturing a CAD system, there are many gaps that are still empty, and there is space for us, for other players in the space to fill there. Matter of creative, just giving you some example. When it's a matter of creating a complex design, it's not just a matter then of creating them. So it's a matter of manipulating them. So all the theory behind digitalization of files that are light and you can manipulate in an environment. And there is much more also in terms of the high fidelity simulation of this design. We are in a trend of digitalization. So preferring simulation against experiment. So as much as simulation we can before going to experiment, but simulating on solutions that are increasing complexity obviously requires more. There are more challenges there. They require more refined simulation systems. So there is a huge, let's say, slice where we can use data. We can use more data-driven simulation there to ease the life of the user, to empower the user even more. I'll just give you an example. I designed something with Toffee or with any other design tool. Then I send it to 3D printing. Then it's rough. At that roughness, which is very hard to capture with mathematical model and with equation, is completely changing my heat performances, my pressure losses. So, and this is an headache for the engineer. Even if it's very close to the optimal shape, you have some physics that are not captured by, you have some, let's say, behavior are not captured by the physical model, that there is so much work to do there to really get to the optimal system and to help the designer.
I see. That is so interesting. Do you want to talk a little bit about data-driven? Because you talked about the term data-driven, right? So we have to talk about AI. Unfortunately, it's like a buzz. Everyone is talking about it. Where do you see AI falling into this term, like generative design, generative AI? I think people mix it most of the time, Where's the distinction? How do you make the distinction?
I will talk just for our space, so without touching a generative AI like ChatGPT or Gemini. I don't know much there, even though I use it a lot. I would say starting with the distinction, the definition. Obviously, is a definition which is still strong in evolution. Usually definitions are made by humans, and now with this very hot and let's say fast environment, these definitions are evolving literally. If you see in Wikipedia, they are, let's say, underlined as probably will change next year. But generative design, it's really a wide space when you include, I would say, any algorithm that is bringing to a solution, to a design, to a digital shape that is morphing something under constraint. Constraint can be the physics of the problem. Constraints can be something that we think later as a manufacturing constraint, but it's really a geometrical constraint. But here we have, the core of these techniques is topology optimization, which is historically the core of topology optimization is physics driven, is driven by the physics of the problem. When we then extend to generative AI, we tend to, let's say, think much more a data-driven approach, which can still fall and definitely can fall into the wider space of generative design. So I would say the first one is wider and includes also physics-driven design. In this context, I strongly believe that the solution is hybrid. Having something that can guarantee the generality of the problem by simulating the physics, and then can guarantee the accuracy of the physics by leveraging data. So having a core that is simulation driven, physics driven, and a core that is data driven. I'll give you an example. In Toffee, you have the same core, which is the solution of the Navier-Stokes equation that drive the optimization, which is the solution of the Navier-Stokes equation. So the same core, it's used by clients in aerospace and clients using it to improve appliances because it's the same physics. Obviously, we can use data, and we use data to capture some phenomena that are proper only of the regime, of the working condition of the aerospace world, and are very different from the data we use to capture some small behavior, some phenomena that are proper only of the smaller scale. So we give generality to the software, which theoretically can be used without data, but we can improve the solution by plugging data-driven approach for classes of problem.
I see. Okay, yeah, that makes a lot of sense. Really insightful, Marco. Is there anything else you would like to tell maybe the engineering audience? Maybe some closing remarks, some motivating words out there, how people can maybe try Toffee?
Yes, definitely. I was thinking about this yesterday while talking to my team, and I'm always there, which is, please spend more time on the problem and much less on the solution. Now we have these tools that are powerful and really require us and require the engineers to sit a second and let's say think that we are moving faster, and experience can be a strong bias, can make us a bit blind to understand what is an optimal solution, what is the next step. So we really need to sit to see what's coming out from generative design, from generative AI, understanding what's going on, like having a slow pace, and then include the new solution, even if they're radical, little by little, into our experience. In terms of the adoption of, just I don't want to be repetitive, but yes, the adoption of design for manufacturing, generative design, etc. shouldn't be scared. We are not replacing engineers, but the opposite. We are thinking, maintaining the engineering world, the engineer in the center of the process. We are just giving more tools to go much faster and much farther.
Excellent. So if anyone wants to check out ToffeeX.com, people can check it out. Is there a trial version for people to check out, or do they have to get in touch with you? How does that work?
No, it's much better if they get in touch with us after a quick discussion, understanding what may be the best usage of the best use cases and application, then we can go from there.
Perfect. I'll put every link relevant to this podcast down in the description, your LinkedIn profile, some relevant white papers people can read through. And yeah, Marco, thank you so much. I hope there will be a second part in the future. Probably there will be, but it was super insightful. And again, if people want to check it out, ToffeeX.com. And yeah, thank you so much.
Jousef, it was a pleasure. Thank you very much for inviting me.